Hello students, welcome back to my channel Explore Physics, Let's Explore. I know you all are doing well. Please take care of yourself. In the previous class I've explained you about the refraction through a glass slab, refractive index and laws of refraction. In today's class I'm going to explain you about the refraction by the spherical lenses, rays to be taken to draw the ray diagrams for spherical lenses, and image formation by the spherical lenses for different positions of the object. So without further delay, let's start the class. So the very first thing I'm going to talk to you about the spherical lenses, that is the types of lenses you may see or you must have seen it. So we have different type of lenses. We have a double convex lens, which is referred as actually convex lens. It is double convex because both the sides are bulging out. Then we have double concave lens. Both the sides are caving in, so it is double concave lens, or we just simply say it concave lens. Then we have plano concave lens. So one side is plane and the other side is concave. So this is plano concave lens. Then we have, if one side is plane, the other side is bulging out, plano convex lens. One side is plane, the other side is convex. So these are different type of lenses and we use it for different purposes. You know the common use of convex and concave lenses. We use it for specs, glasses. This double convex lens or convex lens is also used as a magnifying lens. All of you have seen it, you know. So all these types of the uses of different kinds of lenses, which we are going to discuss a little later. So now I'll explain you the terms related, the common terms related to lenses or spherical lenses. So when we have this double convex lens or simply convex lens here, so it has one optical center. This is the center part, the center point of the lens is referred as O optical center. Same thing happens here with the concave lens as well. So this, the center part is referred as O, the optical center. Now here if you see this lens, this type of, it has two surfaces. I'm talking about the convex lens now. So this side is supposed to be made up of a sphere. So naturally when it is a sphere, it will have one center of curvature, say, let us say that is C2. And this side of the lens is assumed to be made up of the other side, other sphere, and the center of that sphere is called C1, center of curvature. The line passing through these two C's is called the principal axis. So the line passing through these C's, C1, C2 is called the principal axis. So here I am going to take it a little this side, this concave lens. So what did I say? This is O. This side is assumed to be made up of a sphere with center here. This side is made up of the sphere with center C1, C2 here. And this, the line passing through these centers is referred as principal axis. So same thing happens for concave lens also. Concave lens caving in, convex lens caving out, bulging out. So this is about the convex and concave lens. When they have the centers here, they'll have the focus points also. Here also it will have one F2 and one F1, and you know that half of this OC1 is OF1. I may also refer it, not necessarily C1, C2, I can also refer it as 2F1 and 2F2. Here also I can refer it as C1 instead of that 2F1 and this as 2F2. The diameter of this surface, diameter of this refracting surfaces, or the diameter of the lenses or the refracting surfaces, this is called aperture. So aperture of this will be the diameter of this refracting surface. Aperture of this also will be referred as diameter of the refracting surface. The principal axis I have told you, the optical centers I have told you, that O's the center point of the lens. In the mirror it's called the pole, here it's called the optical center. I've spoken about the center of curvatures. It will have two center of curvature. The lenses will have two centers actually. Why? Because it's made up of two surfaces, two transparent surfaces if you may say. And then if I'm going to place the object here, this is the light from the object will pass through the lens, that is refraction, because it can pass, light can pass through the lens here and the image will be from this side. If the light is passing through this, again the light can pass through this glass and the image will be from this side. So it will have two center of curvature and two focus. Same thing happens here. If the object is here, the light coming out of the object will pass through this lens and it will go to this side. Same if I'm going to place the object to the other side of the lens, again is going to make the object. So we are going to see how the images are formed, what rays we are going to take, we are supposed to take while drawing the ray diagram. So let's do that. So I'm going to, if you remember, I've spoken about four rays rather, for the ray diagram for the mirrors. Here I'm going to talk about three rays. Out of these three rays, I may take any two because I have to show the point of intersection where the image is formed. So same thing I'm going to do here. I'm going to take three different rays to draw the ray diagram, which is really going to help me. So the first ray I'm going to take, that is for, first I'm going to take it for convex lens. So let's take this and I'm going to take the same ray. What is that ray? I'll be talking to you. So here this is for the concave lens. So what happens here? The light, and this is the center O for this lens as well. So what will happen? First I'll show the principal axis and C1, C2s here in both the cases for the lens as well as for the mirrors. For convex lens and for concave lens. So the first ray I'm going to take for both, that is the ray which is coming parallel to principal axis. Now it is passing through the lens. So where will it pass? It will pass through the focus point. So here it will have say one F1 and one center of curvature, 2 F1 here. This will also have F2 and 2 F2. So the ray which is coming parallel to principal axis will pass through the F, the principal focus This is refraction, so light is passing through or going through the lens. So the first ray I may take, which is coming parallel to principal axis, and after refraction passes through the focus. What happens, let's see what happens in this case. So here also I will take one ray which is coming parallel to principal axis. Now concave lens, what happens? In the case of concave lens, it goes like this. It diverges. I'll tell you the reason for that. Here we have, say, two F1 I'm going to take, and a little further I'm going to take 2 F1 as well. So here we have 2 F1. Now what will happen? The same thing happens here, that light which is coming parallel to principal axis will pass through the lens and it will diverge. If you just produce it backwards, it appear to come or go through the, F1. So here it is. So we have this ray which is coming parallel to principal axis. After refraction, in the case of convex lens, it passes through the focus, and here in the case of concave lens, it diverges and it appears to pass through the focus. This is the difference in the rays which I have taken for convex and for concave lens. Now because of this, if I am going to take one more ray, say same ray which is coming parallel to principal axis, and after refraction goes like this. This also, if I am going to produce it backwards, this also is going to meet at F2. Now see here, in this case, in the case of concave lens, the rays are diverging, or the ray is diverging. So that is why it is called, the concave lens is also called as diverging lens. Here in this case, if I am going to take another ray, it will be clear to you then. What will happen? After refraction, it goes through focus, and here it is converging. That is why it is called a converging lens. So now you know the difference. Why a convex lens is called a converging lens, convex or converging lens, and why is the concave lens also referred as a diverging lens? Because the ray coming parallel to principal axis, or the rays coming parallel to principal axis, after refraction passes through F, that is, they are converging to a point. That's why it's called a converging lens. Whereas in the case of a concave lens, when the rays coming parallel to principal axis diverge from the lens, and that is why it's called a diverging lens. If you see, if you notice the difference here, see, in this case, in the case of convex or converging lens, it is intersecting, it is passing through F, or the rays are intersecting at this point, the focus. Whereas in the case of concave lens, it appears to pass through F. The ray appears to pass through F, or the rays appear to intersect at F. So here in the case of converging or convex lens, they actually intersect, the rays actually intersect, whereas in the case of concave or diverging lens, they appear to intersect. That is why the images here formed are real images except one case, and in the case of concave or diverging lens, the images formed are virtual and erect images. This is the difference also between the images formed by convex and a concave lens. In convex lens, barring one case, all the images are real and inverted. Here in concave or diverging lens, all the images are virtual images. That is the first ray I was referring to. And now because of this also only, this F is actually referred as real or principal focus, real focus or principal focus, real or principal focus, and this is also referred as real focus. Whereas here they appear to meet, so this is a virtual focus. So at times you may be asked the question, what do you mean by a real focus, or what do you mean by a virtual focus? The real focus in the case of convex lens, when it actually passes through F, or the focus is referred as real focus, or this is actually the principal focus. Whereas in the case of concave or diverging lens, the ray appear to pass through F. So when the term is appear, so it is a virtual focus. This is very common question actually. Now the second ray I am going to take for concave and for convex, both the lenses. The second ray also I am going to show you now. So the second ray I am going to take here first for the convex lens, and then for the concave lens, and see what happens. This is the optical center for convex, and this is the optical center for concave. So what happens, how the images, which ray I am going to take now? The second ray I may take, that is which is actually, this is say 2F2, F2, this is say F1, and here it is 2F1. This is F1, and somewhere here it is 2F1. Here this is F2, and somewhere it is 2F2. So the ray which is passing through F in the case of convex lens, after refraction goes parallel to principal axis. So the second ray I may take with the ray which is passing through the principal focus, and through focus, principal focus for convex lenses, this one. So the ray which passes through focus becomes parallel to principal axis after refraction, whereas in this case, in the case of concave lens, what will happen? The ray which appear to pass, see the difference here. The ray which appear to pass through F, so here I am going to take this, and here it goes parallel to principal axis. So the ray is coming this way, the incident ray is this way, it appears to pass through F, that is the principal, that is the focus, and after refraction becomes parallel to principal axis. So this is the second ray for convex as well as for concave lenses. Now we are going to talk about the third ray. Out of these three rays, I am going to take any two. I may take all three, but it will be too much crowded, all the things, and not very shabby diagram. So I want, at least I'll take minimum two, so that I can show that wherever they intersect, the image is formed here. So the third ray I'm going to take for convex as well as for concave lens, that is, I'm going to show the same thing here. I don't need F1, F2 actually for all these things, but still I'll make. So this is O, this is F1, this is 2F1, this is F2, this is 2F2. Same thing happens here for the convex lens as well. So F1, F2, this is the optical center. So the third ray I'll take, the ray which actually passes through the optical center, and after refraction without any deviation goes back in the same direction, or the same, is going to follow the same way or path. Same thing happens here. In the case of concave lens, the rays goes through optical center and comes back without a deviation in the same path or follow the same path. So these three rays, children, I'm going to take. Out of these three, I may take any two. I've shown you all the three rays. Now after this, I'm going to tell you about the ray diagrams or the image formation for the concave and for convex lenses. So students, I've already explained you about the three rays which are to be taken to draw the ray diagrams. So same thing I'm going to explain now, the image formation by lenses or the ray diagrams for lenses for different positions of the object. So we'll see one, when the position of the object is at infinity. So position of the object is at infinity. So how the diagram what will be the ray diagram for this position? So what will happen, the first ray which we have taken, if you just remember, first ray, which is the ray which was coming parallel to principal axis and was going through F after refraction. So this is the ray, these are the rays which we are going to take. So we assume when the object is at infinity, the rays coming off the object are parallel to principal axis. So I've taken two rays which are coming parallel to principal axis and after refraction passes through this focus F1. This is the image formation when the position of the object is at infinity. We assume that the rays coming from the objects are parallel to each other and after refraction they intersect at principal focus F1. The image form, what will be the position and nature of the image? So position and nature of the image we are going to talk about. So what will be that? Position will be at F1. At F1, what will be the nature? It is to the other side. So it is real, inverted. When it is real, I have told you don't forget to write the term inverted. So real, inverted and diminished, or point size and diminished. So that is the position and nature of the object, of the image. So when the object is at infinity, the position of the image is at principal focus. What is the nature? Real and inverted and highly diminished or point size. What will happen, just the second position I'm going to take, when the position of the object is just opposite to that. So here we have position of the object at F2, the other side. What will happen then? So here the position of the object I have taken is at F2. So I'll write here what will be the nature and the position of the image formed. I'll write that also. Nature and position of the image. So what will that? We are going to see this. So when the object is at infinity, the image was formed at F1. So now we'll see what will happen when the object is at F1 of the focus. So where will be the image formed? So I may take, actually children, I'll be showing you two diagrams for that. So first, when I can take one diagram when the position of the object is at F2, I may say that. So here one, I can take this or these two rays rather, when they are coming or emerging out of the So here we have the point size object, and after refraction goes parallel to principal axis, just opposite to that. So for your convenience, I am drawing it like that, so it's easy for you to recollect. So here we have, when the position of the object is at F2, so what will be the nature? Nature will be other side. So if you remember, in the mirrors we have told the same side will be real and back of the mirror will be virtual. Here to other side the images are called real and inverted images. So this is to the other side, the images to the other side. So nature will be real. When it is real, it is inverted. So real and inverted. And what will be the position of the object? We assume that when the rays are parallel to each other, they're going to intersect, or they're going to meet somewhere at infinity. So the position will be at infinity. That is one case I have taken for the second position. I may also refer one case. Here I am showing you two diagrams actually for this. Same thing for the second only. So here one more ray diagram I can show for this second ray actually. I'm going to one more diagram for second. So here I have the convex lens. Here this is the principal axis, and here I have taken at F2, I have taken little bigger object. This was the point size object, and here little bigger. So I have taken one ray which is passing through O. Remember, this is the third ray I told you. So this is passing through O and coming back in the same direction after refraction, and one ray which was going parallel to principal axis and after refraction was going through the principal focus this way. So it was coming like this. So second ray I have taken, which was actually parallel to principal axis. After refraction, it's going like this. So here we have, after refraction, it is going like this. So these two rays are parallel to each other. They are never going to intersect, or they are going to intersect at infinity. So I may take this when the object I have taken a little bigger, and here I have taken the object as point size object. So in both the cases, this is the same ray actually, position of the object at F2, Here I have taken little bigger object. Here I have taken point size object. But the nature and position of the image will be the same. Nature, real inverted position at infinity. So this is the first ray, this is the second diagram, ray diagram for the image formation. One I have taken when the position of the object was at infinity. Second, I have taken the position of the object at F2. We are going to talk about few more positions of the object, and we'll see how the images will be formed. And I told you before also, in the case of mirror children, if you write it this way, you're going to get, it looks neat also and easy to understand for the evaluator and for yourself also. If the thing's a little neater, you're going to like it. So here I'm going to talk about the third image formation. When the object is, let's see where the object is. I will explain you about the concave lens after this. So here when we have the object this way, every time I have to draw this principal axis. So say this is F2, this is 2F2, this is F1, this is 2F1. F1 I have referred because there is a principal focus to the other side, so I am referring it as F1 and 2F1 here. So second, this is the third image formation when the object was between 2F2 and F2. It is between the center of curvature and the focus where will the image be formed. So I am taking one ray which is going through O, this is O, which is passing through the center of curvature, and after refraction it goes back in the same direction. So this is one ray I have taken. I may take one ray which goes parallel to principal axis, easy no, and goes through this F1. So here we have passes through this and becomes the ray which is parallel to principal axis after refraction goes through F1. Wherever they meet, the image will be formed there. So here they meet after or beyond, rather beyond they meet here beyond 2F2. So when the object is between 2F2 and F2, the image will be formed beyond 2F1. So where is the position of the object? Position of the object is between 2F2 and F2. So image will be beyond 2-1, real and inverted. So beyond 2F1, real and inverted. So this will be the image formed and magnified. So this will be the nature and position of the image formed when the object is between 2F2 and F2. Now see, that is why I am taking the positions like that. When the object is between 2F2 and F2, the image will be formed beyond 2F1. Now I am going to take fourth ray when the object is beyond, here in this case, 2F2. Object is beyond 2F2. So where will the image be formed? So here I have taken my convex lens. Here I have taken the principal axis. Say this is O, you don't have to show it every time. This is O, this is F2, this is 2F2. Say this is F1, this is 2F1, and the object is beyond 2F2. So somewhere here I have taken the object. So I'm going to take the object here beyond 2F2. So I'm taking one ray coming parallel to principal axis, after refraction goes through F1. So the ray which is coming parallel to principal axis after refraction goes through the principal focus. Then the ray which is beyond 2F2, the object when it is beyond 2F2. So I have taken one ray which is parallel to principal axis, goes through the principal focus, and the second ray I have taken which goes through this optical center, goes back in the same way. So here going like this, coming back like this, wherever they intersect. So they are intersecting here. So the image will be formed here. And what is that position? So here the position of the object was beyond 2F2, and where will be the position of the image? It will be between F1 and 2F1. Between F1 and 2F1, this was 2F1, this was F1. That was the position, and nature will be real, inverted and diminished. So the size of the image formed will be smaller than the object. So that is the fourth ray. Third ray was beyond 2f2. So why I'm taking it? Because easier for you to recollect. When the position of the object was between 2f2 and f2, the image was formed beyond 2f1. Here, just opposite to that, when the position of the object was beyond 2f2, the image is formed between f1 and 2f1. Both the cases real and inverted images. Here magnified, and in this fourth case, this is diminished. So this is the fourth case I have taken. I'll be taking two more cases here again. So I'll take fifth and sixth ray diagram. So here what will be the position of the object and the nature and position of the image form. So fifth ray I am taking when the object is at 2f2. So, or at the center of curvature. So here this is f1, say this is 2f2 I am taking f2 and 2f2. Here this is f1 and 2f1. To the other side, f1 and 2f1, and the object is at 2f2. So what will be the position? At 2f2. The position of the object is at 2f2. Where will be the image form? We are going to see that. So again I am going to take one ray which is parallel to principal axis, and after refraction goes through this f1. The other I may take which is passing through the which is passing through O and retraces itself back. So one ray which is parallel to principal axis goes through f1, the other ray which passes through O, optical center, and retraces itself back. Where is the, I'll write it here. Where is the image formed? The image is formed here at 2f1 only. The image is formed at 2f1. What is the position? Position of the image? Position will be at 2f1 to the other side. Real, when it is real, it is inverted and same sized. Whatever the size of the image object is the same sized image which is formed. So the fifth case is when the object is at 2f2 at one of the center of curvature, the image will be formed at the center of curvature to the other side of the center of curvature. It will be real, inverted and same sized. If you observe all these 5 cases which I have taken, every time the image formed is real and inverted. Now sixth case which I am going to take, there the image will be virtual and erect. This is the case, this is the only case in case of convex lens where the image formed is virtual. If you recollect, in the case of concave mirror also, there was one case when the object was very close, orbit was between F and P, the image formed was virtual and erect. All the other cases were real and inverted images. Here also it happens in the case of convex mirror. Convex lens. There it was concave mirror. Here it is convex lens. When other than one case, which I am going to show you now, for all the other cases, the image formed is real and inverted. This is the only case, the sixth case, where the image formed will be virtual and erect. How? We are going to see that. So what will happen here? Again, I am going to take one, that convex lens, and we'll see how does it happen. So this is O, say this is F2 somewhere here, say this is 2F2. This is say f1, this is 2f1, and now the image is, the object is very close to the lens here, and the object is between O and F2. So here it is very close between the focus and the optical center. So where will the image be formed? So we are going to see that. So one ray I am going to take, which is parallel to principal axis, and after refraction, show it here, after refraction goes through F. Okay, so after refraction it is going like this. The other ray I am taking, where it goes through this optical center, if you see, it goes through O, and comes back the same direction. So when the object was between, or is between O and F2, I have shown it like this. This is the object. One ray I have taken which is parallel to principal axis, and after refraction goes through F1. The other ray goes through O and comes back through O again. No deviation in the path. Now if you see, it's like diverging types. So here if I am going to produce it backwards, here I am going to produce it backwards. Wherever they intersect, the image will be formed there. This also I am going to produce it backwards. So the image is formed here. So they intersect here. So the image is formed to the same side of the lens, or the lens, and here it is, wherever they intersect, the image is formed. So here the image is formed, just because of it's wiped out, just draw it in here. So here the image is behind, to the same side of lens. If you see, one ray I have taken which is parallel to principal axis, goes through F1. The other ray I have taken which goes through optical center, and the image is formed. What is the position of the image? Same side of the mirror, same side of the lens, write it here, same side of the lens wherever the object is placed, virtual, erect, and magnified. So we have the sixth case when the object was between O and F2. This was, O and F2, yeah. This is O, this is F2. So when the object was between O and F2, which was very close to the lens, the image will be formed to the same side of the lens. It will be virtual, erect, and magnified. So this is the sixth case of spherical lens, that is a convex lens. If you see the first ray, so you all have these, all you've seen in the in your day-to-day life. If you recollect the first case, when the object was coming parallel to, when the rays were coming parallel to principal axis, they converge at one point. That is the use we take for magnifying lens. That is one. And two, you all must have played with the magnifying lens. If you just bring it, just put it towards the sun and take one sheet of paper here to the other end, you just try to converge all the rays there, the paper starts burning also, because all the sunlight and the heat energy goes concentrated at that patch. You just get the fine bright dot or the patch here. There the image is formed, and in fact if you just put it for a little longer, for a few minutes, the paper starts burning. So the first case when the objects are coming parallel, the rays are coming parallel to principal axis and getting converged to one point. So all these are used for different purposes. We are going to talk about the uses also. So this is all about the image formation or the ray diagrams for convex lens when the object was placed at different positions. So we have discussed the ray diagrams or the image formation for convex lens. Now we are going to talk about the image formation in concave lens. So here we'll take one case when the object is at infinity. Where will be the image formed? We'll see that. So here we have one concave lens, and here we have the the ray which are coming parallel to principal axis. So I am considering two rays which are coming parallel to principal axis. After refraction, as discussed before, it will go or it will diverge. Same thing happens here also. And they appear to intersect at the focus. So here, wherever they intersect, the image will be formed there. So here in this case also, so they appear to meet at this, the focus. So what I have taken, two rays, one ray which is both the rays which are coming parallel to principal axis, because when the object is at infinity, we assume that the rays are coming parallel to principal axis. So I have taken two rays which are coming parallel to principal axis. After refraction goes like this, and when they are produced backward, they appear to meet at this focus. So what will be the position when the object is at infinity? So position of the image will be at f2 or at focal. What will be? It is to the same side of the object, so it will be virtual. Because it is virtual, so it is erect and diminished or point size. Diminished or point sized image. So this will happen in one case we have taken. So the second ray I'm going to take when the object is between 2f2 and infinity. How the image is going to be formed. So here we have taken one concave lens. Here say this is our principal axis, and the object is between 2f to infinity. So one ray, say somewhere here, the object is somewhere here. Say this is 2f2. And so the ray which comes parallel to, I have taken one ray which is coming parallel to principal axis. After refraction goes like this. Okay, it goes after refraction this way. And the ray which is being produced backwards, if it's produced backward, it appears to go through f2, and the other ray I may take which passes through the optical center, and after refraction goes back like this. So wherever they intersect here, there, the image is formed. So what is the position of the image? It is between f2 and O. What will be the nature? Virtual, because it is to the same size of the lens. Virtual, because it is virtual, so it is erect and diminished. Always remember that the images formed by concave lens are always diminished. So images formed by concave lens are always diminished or smaller in size. So these two ray diagrams are there for convex lenses. Alright, so that's all for the day. Stay safe, stay healthy, and a very big thank you to all. Do like and subscribe my channel if you like the content. Thank you.